Okay, so welcome back everyone. Today we're going to talk about signed and unsigned types in C++. And this is going to be a good lead into the next episode, which I'm hoping to make the video on binary that I've been talking about. So in C++ we have this notion of two different kinds of types that some of our data types can be. So we have what's known as a signed type, and then unsigned. Now signed types can be negative or positive or 0. Unsigned types, on the other hand, must be greater than or equal to 0. So this unsigned would contain basically 0 or positive numbers. Now if you remember our subset of data types called the arithmetic data types that we talked about in the series so far, we have within the arithmetic data set we have our integrals and we have our floating points. Now integrals, excluding the Boolean type and some of the extended character sets which we haven't talked about yet, these can be unsigned or signed. Whereas our floating point types, these can only be signed. So by the end of the video, we'll try to answer the question as to why integrals have both unsigned and signed types, but floating points only have signed types. Now, for our integral types, for many of the number types, so like we talked about before, so we have our shorts, int, we have long, and we have long. By default, these integral types, these usually the number types we'll say that represent numbers, whole numbers, these are by default signed in C++. Now we'll see that we can force these types to actually be unsigned by using the unsigned keyword, which we'll see in our editor here in a little bit. But it makes sense that these numbers are signed by default because we saw how we can create negative numbers and positive numbers as well as setting them to 0. And so if you remember in the integral subset of data types, we also have the data type of char. And again, chars just represent a single character. This things get a little bit weird with signed and unsigned types when we're working with chars, because with chars there's actually 3 distinct types. I'm going to write the first one here in a parentheses, so we actually just have the plain, our plain char data type. And I'm going to use U and S for unsigned and signed, but then we have our unsigned chars, and then our signed chars. And so we have 3 distinct types here for chars. Now where this gets a little weird is although we have 3 distinct types, which is just our plain regular char, our unsigned char, and our signed char, there's actually only 2 different representations for a char, which is signed and unsigned. Now before I continue on here and talk about why there's 3 different types of char in C++, you're probably wondering how can we use an unsigned char and a signed char? Like how can there be a signed character with a plus or minus? Well, the reason being is because C++ under the hood is actually mapping characters. So if we have A, for example, it's actually mapping it to a decimal value. So it might say, for example, A equals 1, B equals 2, C equals 3, and I'm just making up these mappings here, but this is essentially what it's doing under the hood, because in binary it's actually representing it as a number, and then it actually it knows the number that represents a particular character. So in binary, if it sees a value of 3, it knows that, and it knows it's a character type, well then it'll map it to C. Same with 1, if it sees a binary value of 1 and it knows that that byte or whatever it might be is a character type, it'll map it to A. And I'm actually going to pull down a table here that I had ready to go. And these are actually what are called ASCII characters. So you can see here, this is just a standard basically of how these values are mapped to one another. But the columns we're interested in here is this decimal column here, this first column, and then the last column here on this char, and that goes for every part of the table here. So you can see that if we go all the way over here to the right, and here's our A, for example, I made up the number 1 that it was getting mapped to, but in ASCII, which is what C++ is using, it's actually getting mapped to the value 97. So in binary, if the compiler came along and it saw that there was a binary value of 97, and it knew that that spot in memory was a character type, it would know to map it to a lowercase a. And you can see that uppercase, for example, is different. So if it saw a binary value of 65 and it knew it was a character type, it would map it to a capital A. And you can see it maps all the way through 127, and if we go down here to the extended character set, there's even more characters that it includes as well. So like 128 maps to this character, 254 maps to a square, allegedly, and then 255 maps to a blank space. Hopefully in the next video when we talk about how we represent these character values and all these values for all the data types in binary, this will make a lot more sense. But I should also have a video down below that should give a brief overview about this, but hopefully in the next video that makes a lot more sense if you didn't quite understand that there. But you can see then that that's how we can justify there being signed and unsigned types for characters, because under the hood they're actually being represented as numbers. And so the reason then that we have 3 different char types is because obviously we have our unsigned chars and our signed chars, but this plain char is actually takes on one of these 2 representations. Now, the C++ standard doesn't specify which representation it takes on by default. It actually leaves that up to the compiler and system that we're using. So, for example, we'll just use C1 and C2 for compilers here. If on this system that we're using compiler 1, if we declare a char, my char, we're basically declaring a char variable here. On this system, on C1, perhaps chars are defaulted to signed types. On compiler 2, we do a char, say my char. Perhaps on this compiler, by default, it actually uses unsigned chars. Now you could obviously force assigned or unsigned on either compiler by putting either a U or an S here in front of it. But the point is that if you're just using the plain char, again, the type it gets sort of represented as by default, meaning signed or unsigned, is totally dependent upon which compiler you'd be using. And I believe that on Visual C++, which is the compiler we're using, I believe chars are actually signed by default, if you want to take my word for it. And so one of the biggest differences or reasons of using either a signed versus an unsigned data type has to do with the range of values that that particular data type can represent. Being signed or being unsigned changes the range that you can basically assign to or represent with a particular data type or variable. And so I'm going to use an integer as an example here, because it's an easy one to give an example for us. So if we draw a number line, put 0 smack dab in the middle here. If you remember back in episode 2 when we talked about all the integral types and the range of values that we get assigned to different data types like integer, shorts, and stuff, you remember that we could assign an integer some value from, it was -2 billion something to +2 billion something. So just to represent that, we're just going to make this easy, we'll do -2b to +2b. It's not the exact number, but it gets the point across. So we could assign an integer a value anywhere in this range here, basically from +2b to -2b. And that was actually a signed integer. That's an example of a signed integer because we have negatives and positives that it can represent. But if we force now this integer variable, so let's say we have an integer variable called int, we'll just call it I. So we have an integer I. Right now, since by default integers are signed types by default, right now we can assign I any value in the range from -2 billion to +2 billion. But let's say we put an unsigned keyword in front of this, so we force this integer now to be unsigned. Well, what would happen then is this range of values shifts. So since unsigned data types can only be 0 or greater, what happens is that now this number line, you can think of it this way, this number line actually gets extended to the right, and let's just say now we can represent up to values of 4 billion. So now when we force I to be an unsigned int here, instead of being able to represent values from 2 billion, excuse me, negative 2 billion to positive 2 billion, now we can represent values from 0 to 4 billion. And again, these aren't the exact numbers for an int, it's just easy to represent when we use rounded numbers like this. But I hope that makes sense, that one of the things that forcing either a signed data type or an unsigned data type does is it shifts the range of values you can represent with that data type. Because again, remember the rules, signed types can be negative or positive or 0, and then unsigned types need to be greater than or equal to 0, which we have here because here's our unsigned range and here is our signed range. And now the reason this shifts like this is, again, I know I keep saying this over and over, but this is going to make more sense when we get to the video on binary, and I can show you exactly how these numbers are represented in binary when your program stores it, and then this will all make a lot more sense. So before we jump into the editor here and start playing around with the signed and unsigned keyword, the last question we have to answer here is, why does C++ support unsigned and signed types for integral types like ints and shorts and longs and long longs, but it doesn't support it for floating point types? Well, to answer that question, we first have to consider why there are unsigned types for integrals in the first place. Why does C++ support unsigned types for integers and shorts and longs and not for floating point types? And the reason being really comes down to a couple factors. Number one, there's a particular operator in C++ called the modular operator, and I'm going to have we'll talk about this when we get to the mathematical operator section later on. So I'm not going to talk about specifically what this operator does now, but this operator works very well when you're working with positive numbers. And so it only makes sense then that unsigned types, which remember the rule for unsigned types, they have to be greater than or equal to 0. So they're always going to be positive or 0. So that would make sense then that unsigned types would work very well with the modulo operator. Now the other thing about the modulo operator is that it's naturally applicable and it works well with integers, and isn't really naturally applicable to floating point types that have like a decimal or a fraction or something like that. Now the other reason that we don't have unsigned floating point types is because if you think about the purpose of using an unsigned floating point type, what are we really trying to do? Or not even an unsigned floating point type, but an unsigned type in general. Remember that number line we drew earlier? Think about what that does when we force an unsigned type on a certain data type. So we use that example of integers, for example. So we knew that the typical range of an integer was approximately somewhere between negative 2 billion and positive 2 billion when you're working with the default signed integer type in C++. And so when we had an int, we declared an int, we'll just say I, the range was negative 2 billion to positive 2 billion. Now when we forced that unsigned type, we extended the positive portion of that range. And we then excluded the negative portion of that range, so that negative portion no longer applied since we had an unsigned type. But we basically extended the positive portion of that range to 4 billion. And again, these aren't exact numbers. I'm just using an approximation here. For integral types, that's very important because with integral types, we're concerned with the range of values. What range of numbers can we support? And we know that with long longs, you can support quite substantially longer or larger numbers than with an int. But when it comes to floating point types, we're not so much concerned with the range of numbers it can support. With floating point types, remember, we're more concerned with precision. we're more concerned with precision for floating point types. And by precision, we just mean, the number of decimal places that a floating point type can support. Now, as a C++ developer, as long as you understand that C++ doesn't support unsigned floating point types, then you're probably good to go. But if if you wanted to know the reason why, to summarize, we talked about the modular operator. So the modular operator works very well, again, with whole numbers, integers, and it also works very well with positive numbers. Well, since integral types are whole numbers like shorts, ints, longs, that's why they have an unsigned types. That way they force to be positive, or I should say 0 or positive, and they're also whole numbers, so they work very well with the modular operator. Well, since floating point types are decimal types and they have like that fractional piece, whatever you want to call it, to begin with, they don't work well with the modular operator anyways. So there's no point to giving it, forcing it to have an unsigned type, because it doesn't work well with modulo arithmetic. The other reason being is because we know that when we force an unsigned keyword on a integral type, it extends the range of positive values for that type. As opposed to, so like when it's signed, it's split evenly between negative and positive, but adding that unsigned keyword extends the range of values, positive values it can support. Now, since floating point types, again, are more concerned with the precision, meaning how many decimal places, for example, can a double or a long double support, something of that nature. It's yet another reason why the creators of C++ weren't really too concerned about supporting unsigned floating point types, since again, floating point types are more concerned with that precision. And I've read several articles too that talked about how, if the language did support unsigned floating point types, there'd have to be some adjustments made to hardware in order to support that new unsigned floating point type. And the effort, it would take to do that versus how much value you actually get out of having an unsigned floating point type just isn't worth the man hours to do so. And as a small plug here, I'm going to be posting in the before you watch section, in the description below, I'm going to be posting this Wikipedia article on modular arithmetic. Again, we're going to be having a section on mathematical operators, all of them, from plus, minus, multiplication, division, and then modulo, and a couple others. But if you just want to skim through this and read about it, go for it. I haven't read this whole Wikipedia article. I've just kind of skimmed through the intro section and some of the congruent stuff before I talked about the lesson today. But it seems to be a pretty solid read, so I'll be posting the link to that again in the before you read section down in the description below. So let's finish off this video then by going into the editor now. Finally, we'll finally do some actual coding, and let's talk about and let's do some examples of some statements with this signed keyword and also the unsigned keyword. So if we just create an int, this is the easiest one to do an example for. If we just create an int, and we'll call it just int I, and we'll set it equal to 1. Well, again, by default, C++ integral types for all of its whole numbers, meaning int, short, long, 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 these are all signed by default. So we could come down here, we could do int I, or we'll do ij equals, we'll say -1. We can come in here and do long k equals 200, and long L equals -200. And again, we can have positive or negative for all of our integral types. So if we come in front of our I here now, let's make some space here. We come right here behind the int, and we say unsigned. So we're forcing, and I gotta spell that right. We say unsigned. We use the unsigned keyword here in front of our int. So what this unsigned keyword is going to do, again, is going to force our integer variable here, our int I, to be an unsigned type. So again, remember, unsigned types can support anything that is equal or greater than 0. So in this case, we're assigning it to 1, which is a positive number. So this works. This meets the condition of what unsigned types can support. Now, if we came down here to our int j and we force this to be an unsigned, you can see that we don't really get an error or anything here on this line from the compiler, or from our development environment. So let's do something here quick. Let's go down to our print statement down here, and let's go ahead and put our I in here. Let's go and put our unsigned int I into this print statement here. That's going to print this out to the console. So if we click our play button, we get exactly what we expect. We get a 1. Now, if we come in here and we replace this with our J and we click play, you see that we get a number here that is absolutely nothing like what we've assigned it to, which is just plainly -1. So the reason being is that for unsigned types, and this is only for unsigned types, the default behavior of the C++ standard, defined by the C++ standard, is that if you are out of range for an unsigned type, there's actually this behavior that takes place called wraparound. So basically, if for an unsigned types we have an int here, an unsigned int j, since the lowest we can go for an unsigned type is 0, since we have -1 here, we've assigned it to -1, what's actually going to happen is when it goes below 0, it's actually going to wrap back around to the largest number that this can support, that an unsigned int can support, which again, if we run it, is this number here. So it will wrap back around to this number, and this behavior takes place. So if we, for example, came in here and put a -2, so now we're 2 under the supported range of an unsigned int, this is actually going to wrap around, but now it's going to wrap around 2 more than it did before. So this is actually going to be a 4 here instead of a 5 at the end. So it's actually going to decrement our number by 1. So let's run this again. Bring up our console here, and there we go. We have 294 instead. And this behavior just continues down the line. So if we did a -3, we would have 293. So if we run it, see, there it is, 293, and that behavior will just continue onward and forward. And so what is really happening with this wraparound behavior? So if we go back into our paint page here and we just draw a little illustration, you can kind of think of it like this, where we have 0 and we have just like this continuous loop where, let's say we have integers that, let's say an unsigned integer in C++ only supported 0 through 10. So we have 0 here as its smallest value and 10 here as the largest value that is an unsigned integer would support. So if you assign, for example, let's say we had int I is equal to 1, well then we would just have a 1. We would just assign it to 1. And that's fine, you know, that's in the supported ranges of unsigned ints if unsigned ints in C++ supported from 0 to 10. Now on the other hand, if we support, or if we set another integer, let's say call this one j, we set this one to -1, well, this is where we're going to see that wraparound behavior, because it's less than 0, which is outside the supported range of our unsigned integers. And so what's going to happen is it's actually going to wrap back around this direction in the loop. And so it's actually going to set it to 10, which is actually our maximum. And this behavior is going to continue just like we saw before in the editor, where if we set it to -2, it'll actually continue around this direction in the loop, and it'll set it equal to 9, set it equal to -3, it'll be 8, and it will just continue that behavior all the way around, back around to 1, and then 0, and then if the negative number was a large enough negative number, it would just continue the same exact path back around again, and it's going to keep wrapping around and around and around. And likewise for the other direction, you know, if we set, so 10's our maximum here, right? If 10's our maximum, and we had another int, I'll just call it R, and we'll set that equal to 11. Well, since 10 is the maximum, instead of now looping this direction, you know, to the left, we're actually now going to loop around this way to the right. And I set the arrow a little bit too far there, but it would actually be equal to 0 here if we set this equal to 11, since 0 is the minimum that our unsigned integer supports and 10 is the maximum. And since we're 1 over the maximum here with 11, we would set it equal to 0. I most definitely went a little bit overboard on the lines and drawings here, but I hope that makes sense. I hope that wraparound behavior makes sense. It's actually quite simplistic in nature, of of how that works. Now the way it's actually calculating that is actually has to do with modulo or arithmetic, which we'll hopefully talk about when we get to the modulo section, or the mathematical operator section, if I remember it. But it's actually using that operator to calculate the wraparound value. But yeah, hopefully we'll see more of that later on. So if we come back into the editor here, and we write the keyword sign now, so now we're going to force the data type to be of the sign type. We'll write j, we'll say k equals 1. It's exactly as we expect, and we could do the same thing, signed int, we'll say l equals -1, and we know that's fine, because by default, again, in C++, the integral number data types are signed by default, so you can obviously make them positive or negative. Now, one interesting thing to note, though, is that overflow, like we saw for unsigned, how that has that wraparound behavior, that is not the case for signed. If signed values overflow, and for signed values, that would be if it was greater than its maximum number of data types, so an integer, for example, could support, or less than the minimum amount that it could support, so some large negative number. It doesn't actually have that wraparound behavior. It actually is undefined. So even though many compilers will actually treat it the same as unsigned, where it'll actually just wrap the value around, that's not the case for all compilers. So you can't really depend on that being the behavior of signed types, because as you move from different system to system, so if you move your code base from one compiler to the next, you might actually have different behavior on different systems. So it's what's called non-portable code, meaning that if you took this code again and moved it from one system, so that, like Visual C++, for example, to a different compiler, maybe GCC, it might not work the same. And so basically, being that it's undefined, overflow behavior is undefined. And I shouldn't confuse this here saying that k equals 1 is undefined, but we'll say overflow equals undefined. You should never rely on this type of behavior for sign types. You should never program in such a way that you're depending on sign types to wrap around for any reason, because the actual implementation, or I should say the actual behavior when you're actually running your program, could be unknown. Now again, on our Visual C++ compiler, which we are using, this actually will wrap around. It is the behavior that the compiler uses, but we still don't want to program in that way, that we rely on that, because if we move again to a different compiler like GCC, it might not behave the same. So in summary, for sign types, don't overflow the value and depend on the behavior that you're seeing in your specific compiler, which for us is the Visual C++ compiler. You can only ever really depend on that for unsigned types to have that wraparound behavior, because it's actually specified within the C++ standard that that's what will happen. That's the behavior it will take on. I'm not going to say too much more about signed number types that are of the integral type, other than what we've said, just because we've already seen this before. Since by default in C++, integers are signed by default in C++. You've already seen how these behave with maximum and minimum values and their ranges and such. So not too much more needs to be said about that at the moment. One thing I do want to point out, though, and if you try to use the signed or unsigned keyword for, we'll just use a float, for example, f equals 0, you'll notice here that your IDE, your integrated development environment, so it would be Visual Studio, actually throws you a syntax error here. It says invalid combination of type specifiers. So even though floating point types are signed by default in C++, it doesn't even let you use the keyword here, because we already know that floats can't be unsigned, as we talked about before, and it'll give you the same exact error here. But because these are signed no matter what, this actually won't even let you specify a type here. It'll give you this error, invalid combination of type specifiers. Just a bit of information I wanted to throw your way there. The last thing we need to talk about actually are the character types, so chars. So we'll write char c equals a, just to get us a char in our editor. Now, if you remember in C++, there's three different types of chars. So we have our plain char here, which the representation, meaning signed or unsigned, of a plain char is dependent upon the compiler you use. I believe in Visual C++, which is what we're using again, I believe it's signed by default. But we can also come down here and say signed char s for signed. We'll say that equals to s, and then we'll also say for an unsigned, so unsigned char u equals, we'll say u. So if you remember from previous videos, we talked about how in C++ the standard char set, so just chars, is composed of 8 bits. So 8 bits. Which means it can take on 256 different representations of values. This math will make more sense in the next video when we talk about binary. But when we talk in terms of unsigned chars, I'm just going to use uchar for short. This means that unsigned chars can represent anywhere from 0 to 255, since 0 to 255 would be 256 different representations of values, and we know that unsigned types have to be 0 or greater. On the other hand, signed chars, the C++ standard doesn't necessarily define how signed types need to be represented, how their values need to be represented, but what it does define is that the range of negative and positive values needs to be identical, and it needs to be even. So signed chars can actually represent values anywhere from negative 127 to positive 127. And again, the reason we're referring to characters here in terms of number values is because if you remember from that drawing we made before, I don't think I have it on this page anymore, but if we, for example, have a char, let's call it C, and we assign it to the value of the character A, well, that A under the hood could be mapped to a number value. It's how basically how the language, it's how our computer represents this character in binary or in machine code. So again, maybe A is mapped to 1. If we had another one that was, we had a B character, remember again, perhaps the B is mapped to 2. And basically, this standard character set then, all of the characters that it can represent are mapped to values all the way from either 0 to 255 or negative 127 to positive 127, depending upon whether it's unsigned or signed. So I was actually going to wait till the arithmetic operator video to show this, but I figured now might actually be a good time to give you a little sneak peek of something here, and then we can always come back around to it. So if we assign, or if we declare, I should say, a variable, int type variable, and we'll just call it val for value, and we assign it to 1, right now we would expect this integer variable to have the value of 1. So if we print it out here, and I'm actually going to have to comment these out real quick because we'll get a redeclaration error otherwise. If we print val out, we should expect to see 1 in the console. And there we go, we get 1. Now, if we come back over here to where this assignment statement, and instead of doing 1, we do 1 plus u, our u variable here, our u variable that's assigned to a value of the character u. Let's see what happens here when we do this addition here and then print this variable out. Enter. So you'll see here that we get 118. So why is that? Why do we get 118 when we add 1 and our variable u together, which we know is of type unsigned char? Well, the reason being is if I pull down that handy dandy ASCII table that we were looking at before, if we find u in the table, which is right here, and we go over to the left, we'll see that it's mapped to the decimal value 117. So remember how I said that characters in a computer are basically mapped to a decimal value, a number value, to be represented in binary. We can see that here u is represented to 117. So that's how kind of we come up with this 118, is we're actually adding. So when we take a number and we add it with a character, this character actually gets converted to its integer value that it would otherwise be mapped to, which in our case for you is 117. That's how we come up with 118, because 1 plus 117 is 118. With that, I think I'm going to wrap up the video there on signed and unsigned types. We'll definitely be coming to these later on in the series, so we're not done talking about them yet. There'll be more to come, and I'm sure we'll learn some more things about them and how to use them. As a general rule of thumb, only use unsigned types if you know that a value can't ever be negative. I mean, obviously, because they only go from 0 and upward. So only use unsigned types if you know for certain that your value cannot be negative. But yeah, next time we're going to be talking about binary, which is that video I've sort of been hinting towards for a while. There's still a lot more to talk about with data types, like type conversions and strings and arrays and everything else that goes along with that. But I really want to talk about binary because I want you to be able to see how data is represented under the hood in C++ and how it's represented on your computer, how it's stored in memory, because binary is in fact machine code, and it's how your computer represents all of these different data types. So be on the lookout for that, and I will see you then.